Okay, so here's what we got so far to talk about today. We're looking at a bunch of colligative property problems, particularly in the context of the lab. Hey, come on in, grab some chairs. I just started recording, so I'm being a little awkward.
You're only recording the left half of the board.
Okay, it rotated, huh? Yeah, I bumped it. Okay, so. No, you can. Okay. You can grab a chair. You're all good. We can make space. Everyone can tuck bags and things underneath chairs and desks, so we got more space. So, colligative properties. Let's talk about what's going on in the lab. What's happening generally with colligative properties? Without getting into the deeper theory about why in terms of entropy and stuff, we'll get to that later. Fundamentally, what's happening is when we have the freezing point, I'm going to do it in terms of freezing point because that's what we did in the lab. You could do this for boiling point, osmotic pressure, and vapor pressure. But when you have the freezing point of a solution, right, adding stuff to a solvent, right, the freezing point of a solvent, right, if there was no entropy effect, these two things would be perfectly equal to each other. The freezing point of your solvent, in our case water, would be equal to the freezing point of water with stuff in it. But there's a change that happens. That entropic term comes in, changes the way this happens, and we end up lowering, that's why it's a subtraction, we end up having a freezing point lowering. And in order to understand that freezing point lowering, we have a couple different things we have to think about. Hey, come on in. Right? We're going to care, I'm going to write it in a different way than we usually write it. First, we're going to have some constant that's particular to the material. It's a material property. We look it up for water, whether it's the freezing or boiling. We could look it up for ethanol. We could look it up for glucose or you know, anything. Anything we want to freeze or melt, we can look up some values for it. Then we're also going to care about the concentration. We're going to look at the moles of solute. Now, we want concentration, so we're going to use a special unit of concentration because we want something that's not going to change with temperature. So rather than using our typical of moles per unit volume, we're going to do moles of solute per kilogram solvent. All right. This term gets a special name. This term here, I use script M, and that's molality. It's a new unit of concentration that we've introduced because of the particulars that we run into with big temperature changes causing volume changes, needing to get a different unit. The last thing we have to take into account is the fact that our solute could be a covalent compound, could be an ionic compound, could break apart and put extra things into water. And since what we're worried about here is this entropic idea, the things being put into water matters. So we have a counting number, I, that tells us how many things are going into the water, right? If we put one thing in and it breaks apart, we got to count it as 2. And so this thing, I don't know why I made his name lowercase. This is called the Van Hoff factor. Now, the other catch that we run into is this is essentially what we're doing. We can, if we've got Kf and we got the molality, we can solve for I. If we've got I and the molality, we can solve for Kf. If we've got I and Kf, we can solve for the molality, right? We can do all of this switching back and forth. The last thing that we have to deal with is the fact that our concentration is usually given in, let's just say X grams of solute per 1 gram solvent. All of the bottles we had for ours, this is a really typical way we see concentrations actually, because if you wanted to make hundreds of solutions or really heavy solutions, you just measure, you get 2 containers, you don't care how good the containers are, just as long as they can hold liquid, you measure how much weight of this one, how much weight of that one, dump them together, your solution's made. No like special glassware with the meniscus and like, you know, bouncing and being like, oh, order of operation because that thing's going to add more volume. None of that, right? You just weigh the 2 things, dump them together, done. It's really nice in a practical sense. Calculationally, conceptually, this unit's not that useful, but experimentally, this unit's really useful. So we need to get our experimentally practical useful to molality. And that's where we multiply by 1,000 grams solvent per 1 kilogram solvent. And then we multiply by 1 over molecular weight. Now, I'm going to kind of crunch this all down into one equation, because I want to kind of demonstrate how I think about, we've got several different questions, which to me are kind of all the same question. And so I'm going to crunch this down to one big equation. We're going to look at it and say, okay, what happens with this equation? So we've got, here, I'll switch colors to be dramatic. So if we crunch this down mathematically, we get TF solution equals TF solvent minus KF times X grams over 1 gram times 1,000 divided by molecular weight times I. Now, typically what we're going to do to start is we're just going to subtract these two things from each other. So I'm just going to move this over. I'm going to subtract that, turn that into an equal sign. Oh, wait. Nope, I can't get rid of that negative sign, sorry. Subtract that over, equal to negative. Don't mess up your negative signs. So now, you know, if our water is freezing perfectly, our solvent, that's just a 0. Now, most of us, we had non-zero freezing points for our water. That was part 1. So we just take the difference of those two. They call this difference would be your corrected freezing point. Use your corrected freezing point. The reason I see all of the problems in this as the same is this X grams we have, this number is on the bottle, right, whatever we got. That X is on the bottle. So there's 3 variables we have, KF, molecular weight, and I. They have physical meaning, they have different things they're trying to talk about, but essentially, after I make these 2 measurements, I look on the bottle, I just have to rearrange the equation for which one I don't know. Part 1 was just getting this solvent number. Part 2 essentially said, hey, take this ethanol solution, freeze this ethanol solution to get this KF value for water. We know the molecular weight of ethanol. We know the concentration on the bottle, and we know for ethanol, because it's a covalent compound, I is equal to 1. So then the only thing we don't know is KF. We divide everything over, get KF alone, and solve. For the second part of part 2, it says now take some other solutions where we don't know the Van Hoff factor. We have an idea of what it should be. And we talked about this in class where it's like, if it's sodium chloride, for example, we put sodium chloride into water, but it breaks apart into 2 things. And so the Van Hoff factor would take that 2 into account. In that case, we know it's sodium chloride. And we've got our concentration in the bottle. We know KF for water, and we know the molecular weight for sodium chloride. We move everything over. We solve for I. If sodium chloride is behaving perfectly in water, I is equal to 2, and we're all set. Well, I should say 2 things. If we do our experiment correctly, and sodium chloride is behaving correctly in water, the way we expect it to. The place where this gets interesting is some things dissolve better or worse in water. Some things, you know, this assumption that the ions are going to completely separate and not interact with each other at all is an oversimplification. So we don't always see the Van Hoff factor get as big as we think it should. Right? The sodium chloride, maybe it separates out completely. Maybe it only separates a little bit and they're still associated with each other. They can separate and come back together. Because there's a plus and a minus in water. They could be interacting with each other some. For that reason, our Van Hoff factor might be a little bit lower than 2, experimentally. Ideally, it's 2, right? If we say solutions are behaving the way they should, everything's doing fine, that would be 2. And then the last experiment says, hey, we're now doing this for an unknown compound where we've got the concentration on the bottle. We're using the KF of water, measuring both temperatures. And we don't know the molecular weight, though. However, we're told it's a covalent compound, so the Van Hoff factor is going to be 1. So then I just rearrange all of this to get molecular weight by itself, and I can solve it that way. Okay, so I really have 1, 2, 3. I have 1, 2, 3 variables. We're always given this grams per gram on the bottle, so we never had that as an unknown variable. We could have, though. We could have just handed somebody a solution and said, hey, we don't know how this solution was made. We know it's sodium chloride. We know its Van Hoff factor is 2. Can you tell me what the concentration is by trying to freeze it? And we could have done that as well. There was actually like a post-lab question where you were supposed to solve for that X grams. But, you know, during the lab, we just had those 3 different parts. So that's what we're doing. Let's go ahead. So that's kind of, for me, that's why I looked at this and I was like, finding I, molar mass, those are really the same problem, right? They're the same problem. It's just how we're rearranging this information and how we're understanding what's going on. So questions about that. And is this also what you two wanted to talk about?
Because the question that asks about how the Van Hoff factor experimentally is less than ideal,
okay.
Ours was more.
Weird. You know what that usually means?
What?
Contamination.
Okay.
Right, so we'll talk more about that when we do our finding I calculation. Should we go ahead and do a calculation? Okay, I'm going to erase a bunch of this. Who's got data where we want to do it together? I'm going to rewrite that equation in black at the top of the board. So let me not erase it. T final solution minus T final, T freezing solvent is equal to negative KF, and that negative is supposed to be there, right? I subtract that over. Yeah, this is fine. Because this is going to be a negative number, because that's always going to be, right, because that's going to be lower, then you're going to have lower minus 0, so that's negative. The negative will cancel out. Okay. Sorry, I just had to do a quick thinking. I'm going to rewrite this as x grams per gram divided by times 1,000 divided by molecular weight times I. I'm just trying to crunch up my stuff a little bit more. Gram per kilogram. Okay. So let's go ahead and let's look at this with some data. Who's got data we want to look at? Yeah.
Okay, so we did unknown A and the mass.
Oh, that's for the molecular weight one. I wanted to do a finding I one first. And even if you got it right, we can use your data still.
Okay, yeah, I can do the finding I.
Yeah.
So we did sodium nitrate.
Okay.
And the mass of the solute dissolved was 0.0170.
Okay.
And then the measured freezing point of solution
Hey, come on in.
was negative 5.1.
What was your freezing point of water?
Negative 0.5.
Freezing point constant for water is 1.86?
Yeah.
Okay, so we got our 0.0170, 1,000. Our Van Hoff factor is what we're solving for, and we need the molecular weight of sodium nitrate. So we're going to do 16 times 3 plus nitrogen plus sodium. It's 85 grams per mole. So once I plug in all of that data, notice I is the only thing I don't know. Now, ideally, if sodium nitrate is behaving properly, as we expect it to, sodium is a +1, nitrate's a -1, Nitrate is a polyatomic anion. I'm expecting this to split into Na plus and NO3 minus. That would lead to a Van Hoff factor of 2. Because I'm seeing it split into two things. The fact that it's ions doesn't matter for us. We're really just worried about this entropic effect. How's this going to affect the phase change aspect of it? So the fact that it's ions, that part doesn't matter. It's the entropy, just there's more things in solution than we thought. We can go ahead and crunch some of these numbers. 5.1 negative plus 0.5. That's going to get us negative 4.6 is equal to, I'm going to multiply all these together. 0.017 times 1,000. I'm not going to do it all together yet. Hang on a second. Divided by 85. Oh, weird. Negative 1.86. My molality would end up being 0.02. And then my Van Hoff factor is the thing that I'm solving for. So I put all that together to get to molality. I can now get rid of the negative sign on both sides. Take care of that. Divide everything over and see what I get for I. Times 1.86.
You should get like 1.8.
Inverse. No, I'm going to get something weird. Did I mess up? I'm getting 12.3. Is that what you got?
Yeah.
Oh, good grief. Okay.
Ours is overshot.
This is a great example for talking about, hey, that's not supposed to happen. So what does this mean? And I think I talked to you about this, right, during class. Because I saw that and I was like, oh, well, something's not right. So here's one of the nice things about LabPal. LabPal will say, hey, you did your calculation correct from the data you gave me. Looks like your data's terrible, but go with it. Right, so there's kind of two different things that are going on here. From the experimental data we recorded, we got some answer. LabPal agrees we're doing the calculation correct. If I saw 12, if we didn't have LabPal to tell us like, oh, 12 works for your data, I would frantically be searching through your calculations to figure out what you did wrong. Because 12.3 is a really weird Van Hoff factor. So what does that mean? I was expecting 2, I got 12.3. Works for your data. Something's wrong with your data in this case. Now, how can I say that with so much confidence?
Because it should be less than 2.
2 should be the maximum for this thing breaking apart in water. So 2 is the maximum, most ions in solution. Things that could be going on. When I see a Van Hoff factor of 12.3, because this is the maximum, that's the most it could break apart. So the question for the one you were asking about, of like, you know, why do we expect a Van Hoff factor less than the ideal? Right, the ideal is the maximum it could break apart. When you start to do real world solutions, sometimes it doesn't break apart as much as you think it will. Temperature has an effect on how soluble things are. You can have if you have concentrations that are higher, this isn't very high concentration, but higher concentrations start to have additional effects as well. There's all these little hiccups that can happen. But this is the maximum it can break apart. So how do we explain 12.3?
The negative 5.1 temperature. That seems.
Yeah, but like conceptually, how do we explain this? Like we know it comes from the data. And I don't know if any of you have had to calculate a percent yield before. But there's this thing, it's a Chem 124 lab. You're supposed to, is it 124 or 129?
9.
Is that the percent yield one?
Yeah.
Okay, so there's a lab eventually where you have to calculate percent yield. Can you hand me my water? Thank you. There's a lab where you calculate percent yield. Oh no, you do it in 124 as well, limiting reactance lab. And I have a bunch of students who calculate a percent yield over 100. We're actually going to do a lab like that in 125 as well. Which means your reaction is making more than is theoretically possible. Right? We're getting more things in solution than theoretically possible. And, you know, there's two options. Option one is we've discovered a flaw in chemistry and science, and we need to study this more because we've discovered something that super ionizes the water and creates this huge freezing effect that we don't expect. Or you got a bunch of junk in there that you didn't take into account. In addition to your sodium nitrate, you spilled some sodium chloride in. You got too much. You got something else in there. If you use tap water instead of deionized water, tap water has all kinds of junk in it, right? And I know we checked things, but this is what this communicates to me, right? If we've got a Van Hoff factor above 2 for sodium nitrate, there's some other things in there. There's approximately 10.3 other things in there that we didn't take into account. That's my hunch. Now, fortunately, we don't grade the labs on scientific accuracy. We grade them on conceptual understanding. So that's why if you do the calculation correct, even if you get an answer that doesn't really make sense, as long as you can explain why it doesn't make sense. Say, well, we got this from our data. We know this doesn't make sense with our data. We should do the experiment again. We just don't have time in the quarter. So go do it at home. No, I'm teasing. Make sure you make the solution to exactly 0.0170, which is easy when it's grams per gram. No, I'm kidding. If we had more time, we'd do it again. A lot of people, I found a couple students who were having huge issues with their freezing points because they were using the DI squirt bottles at their desks. And I was like, hey, did you fill that up? And they're like, no. And I'm like, okay. Like, it should be DI water, but based on the freezing point we're seeing, I'm guessing it's not. They dumped it out, they refilled it, and then it worked. And so there's that possibility that somebody trying to be helpful filled up the DI water bottle without DI water. In a lot of our experiments, it doesn't matter. The reason we always say use DI water is to get in the habit of taking that into account. In this experiment, this colligative properties experiment in particular, I was like, oh, this one's going to be a problem. And so we actually checked it. We dumped out that DI water, and it actually made it work. So
For the question that's like, why is the actual Van Hoff number typically lower? If we got higher, do you want us to answer why it would be higher? Or?
I would do both. And I'll add something that says if you got higher, explain, right? You can explain, oh, we expect lower, typically lower, right? Because we see this kind of like not full ionization, we see concentration and temperature effects that make it so it doesn't completely split into exactly two things. It splits into like, you know, some of the things don't split up as much as the others, and so we see something that's like 1.8, 1.7 instead of 2. And then you can add to that, I saw a value larger than 2, which I know doesn't make sense.
Okay. Because of all the factors.
Yeah. Likely contamination. I should do the experiment again over the weekend for fun. But you don't have to. But you could. But you don't have to. Questions about that? Should we try it again, but for molar mass this time? Okay. Let's try it again, but this time for molar mass. I'll do it in green. Should we do your data again?
Yeah, sure.
Okay. Do we want to use someone else's data for the molar mass one?
I'll volunteer data.
Okay.
I don't have an answer, but I'll volunteer data.
Let's volunteer your data and let's see what answer we get.
I did C. The molar solution is 0.333. The uncorrected freezing is -1.1. Corrected is 1.8. -1.8.
So your correction, was -1.8? Your correction was 0.7?
0.7.
Okay. And we know this is a covalent compound, so the Van Hoff factor is 1. Notice after I put all of that data in, the only thing I don't know is molecular weight. So this is frustrating because, you know, I can't calculate a molality and plug it in, but I have all the information necessary for rearranging to solve for that molecular weight. We also could have done this in 2 steps, where I take my corrected temperature, solve for molality, and then say molality is equal to this thing with the unknown molecular weight. That's a really common way to go about this problem. It makes more sense in the context of the experimental data we have. So let's look at it that way, right? So if we were looking at it that way, I'll do it in purple. We do 1.1 minus that gets us negative 1.8 is equal to negative 1.86 times molality times 1. And then we divide by 1.86, divide by 1, we get a molality that's almost 1, right? We don't know what that means. 1.8 divided by 1.86 divided by 1, we get 0.9677 is equal to molality. And then we can bring down that equation we have in green from above. So this makes sense from the data we collected, this work in purple, right? Because this I measured, this is my equation, I don't know the molality. But then we use this chunk here and we say, okay, I know that molality is also going to be equal to 333 times 1,000 to get it into kilograms, divided by the molecular weight to get into moles.
Wouldn't that mean that the 0.9677 is your molecular weight?
No, because I still have to do the rearrange, right? I'm going to multiply by molecular weight divided by the 9.677. I got to take that 0.333 into account.
Oh, okay.
So then we just do a little rearrange, and I'm going to end up with molecular weight is equal to 0.333 times 1,000 divided by 0.967, and we'll get an answer for that. Inverse times 1,000 times 0.333. Okay. 344.1 grams per mole. Now, when I do it on the board with all of you, it looks real easy, right? I've done this class a bunch of times. If you had done this class 8 times, you'd be able to do it pretty easily as well. It's easy when I do it on the board because I kind of have this flow of thought, these things that I'm thinking about as I'm going through it. I can think about it experimentally, or I can think about it, that equation in black, where I just thought about it in terms of what's my maximum number of variables that I have to solve for, right? I got this equation, I got 1, 2, 3, 4, 5, 6 variables. As long as I have 5 of those 6, I can solve for the last thing. And that's what's going on over and over again. This work in purple is a little bit more experimentally relevant, so that's also useful. 341 is a completely reasonable molecular weight for these organic compounds that we're dissolving into water.
So what would that be like?
I don't know. I know there's a list of like 5 or 6 things that they use. They're like pretty large sugar-like molecules, so things that dissolve in water well, but have different molecular weights to them. So like fructose, glucose, sucrose, galactose.
Oh, so you don't know what the solutions are?
No, not off the top of my head. I think I have it in an answer key someplace, but I don't know off the top of my head.
Alright.
And I don't actually care what they are, but I want us to be able to get the molecular weight. Now, we could do some further analysis someday, right? We could say, okay, I want to know, after I've got the molecular weight, can I figure out what the chemical compound is? And, what's that?
Technically?
Yeah. Like, if I really wanted to know, I would probably evaporate the water to get some solid material, and then I'd do combustion analysis of the solid material, kind of like we did in 124. So I could get a %C, %H, %O, and then use those percentages of carbon, hydrogen, and oxygen to figure out what the empirical formula is. We did that in 124, though. We don't need to do that here. Here, the emphasis was understanding this idea of freezing point depression, Van Hoff factor, and molality. So we just had a different emphasis this time. Questions about that? Okay. We got some questions about delta G and precipitating solution. Is there anything else I should add to the list?
I had a question about the charts or
The IMF
the
charts?
IMF stuff. Yeah.
Okay. that might be useful when we're talking about this delta G idea, so that might loop in really well. I'm going to erase what's on the board for the colligative lab. We are done with that. Yeah? Okay. Oh, the purple always has trouble erasing.
So why'd you use purple?
Because I like it. There's things I like about it and things I don't like about it.
Well, it's like, you're like, it always does this. I'm like, why'd you use it?
Because it's still nice to have other colors. Okay. Who had the delta G question? Do you have a specific one? No.
Just in general.
Just in general. Oh, shoot. Who asked about the precipitation one? We can do it for that. Okay, let's do that one. Do you have a specific question?
Yeah.
Let's read it out.
It says, consider an insoluble salt in which the absolute value of the heat of hydration is less than the absolute value of the lattice enthalpy. What are the signs of standard Gibbs energy, enthalpy, and entropy of precipitation?
Okay, so as you all know, I'm terrible at doing the precipitation version. So I'm going to put this one in timeout just for a moment, and I'm going to do it for solubility.
Why don't you just have it as negative solubility so it's in participation?
It will be, but I'm going to do a solubility and I'm going to flip all the signs.
Oh, okay.
So I'm going to do it for solubility, so I'm going to look at a solid going to aqueous plus aqueous, right? Usually some plus, let's not put pluses minus, right? I'm doing a solid going to aqueous ions. This is the opposite of precipitation. Precipitation would be going the other way. So when I do this, an insoluble thing would stay as solid, right? That would be product favored. Product favored would mean delta, sorry, that's not product favored, that's reactant favored. That means the reaction is not happening. If I put whatever solid this is, this insoluble solid into water, it stays as solid. Or if I put the ions into solution, it would become solid, but it's going to be the solid thing. So for how I have this written down, that would be a positive delta G. It's going to, it's not going to have leftover energy. The reaction is not going to proceed forward. It's non-spontaneous. Okay, so that's the delta G. For the delta H, I know that it's going to be these two things added together. Delta H of lattice plus delta H of hydration. And we saw this with the warm-up question in class yesterday, where without extra information, I can't really tell. I know the lattice is positive, the hydration is negative, but I can't say more than that. Except this problem, we actually have information. The lattice is going to be bigger. The hydration is going to be smaller. And so I draw it in this kind of cartoon way where I draw a really big plus and a little minus on purpose. I don't know how big or how small, but I know one's big, one's small. I know the lattice is always positive. I always have to put energy to make that happen. Hydration is always negative. Thinking about the solubility reaction. Then I can tell that my delta H overall is going to be positive. It's not quite as big of a positive, but it's still positive. Okay, so I've got my delta G from the fact that it's soluble. I've got my delta H from the lattice and hydration being put together. And now I can look at my delta S. My delta S, let me write it out properly. So to get my delta S, I look at delta G equals delta H minus T delta S. If delta G is positive and delta H is positive, delta S could be anything, right? It could be negative and any value, or it could be positive and kind of small, right? T delta S needs to be smaller than delta H if my delta G still ends up positive. But it could be negative in any value or positive and small, so I can't tell. Could be big, could be small, could be positive, could be negative, I don't know. So my delta S is just going to be unknown in this case. My hunch is that it's going to be close to 0, because when we have like we had in the warm-up question, The entropy of breaking the lattice apart is positive. The entropy of hydration is negative. Those two things might balance, usually are pretty close to each other, balance out pretty well. But I just did it for the wrong problem, right? I just did it for solubility instead of precipitation. But now I can take this out of Orange Prison, and I can just say, okay, for precipitation, I'm just going to flip my signs. Delta G is going to be negative. Delta H is going to be negative. Delta S, still unknown. And for me, that process of doing solubility first every time is just conceptually easier for me. Rather than trying to remember what's happening in a different way with precipitation for the delta G, the delta H, the delta S, like all of those things, always thinking about it in terms of the solubility reaction, and then recognizing I'm just going to flip the reaction to get it to be, precipitation. I'm just going to have the arrow going this direction. I'm just going to flip everything. It's just conceptually easier for me. And the reason I almost always do solubility first is this is the one we use in later chemistry classes more often. This is my Chem 129 equation sheet, and I've got this big list of solubility values. So we always do it for solubility. Because we know precipitation is just the flip of it.
Solubility is just negative precipitation.
Pretty much.
Or precipitation is negative solubility.
Yeah. Yeah. So that's the way I think about it. This did not bring up since this was an ionic solid, this was an insoluble salt, we didn't have to deal with the IMF's chart. But we did talk about delta G plus minus. Did that help? And we talked about the insoluble precipitate. It helped?
Yes.
Okay. Do we want to talk about this anymore? I guess we'll talk about it again when we do the IMF chart. Okay, so one of the things that becomes important to realize is that this was for ionic. Right? This was our ionic consideration. And I had this realization 2 years ago while I was teaching Chem 124. There's a bunch of pet peeves I have in chemistry of like things that I really stress, like don't do this wrong, make sure you pay attention to this. One of them is not, like getting precipitation and solubility mixed up. But while I was talking about my pet peeves, I realized there's two things. One is my pet peeves are things that I did wrong when I was a student, and I was mad that no one corrected me. So I make a big deal about it now because it was I didn't get made fun of, but like in my upper division classes, there were definitely people who were like, why don't you know this? I was like, I don't know why I don't know this. But what I realized is it all really comes down to identifying whether it's ionic or covalent. Like making mistakes in recognizing whether something is ionic or covalent is a really big deal because just like we're going to see right now, ionic compounds kind of have a different set of trends than covalent compounds. It's still delta H, delta S, delta G, but our experimental kind of practical understanding of those things comes from a different direction for ionic compounds versus covalent compounds. So recognizing that this is how we think about ionic compounds is really useful. And if we want to think about covalent compounds, we have to recognize we're looking at covalent compounds. And then we say, okay, I've got a different set of logic that I use for covalent compounds because it doesn't really have a lattice. It has intermolecular forces, not a lattice. So I need to change the way I think about it. Should we look at a covalent compound? Let's look at a covalent compound. I need to pick two covalent compounds that we're going to try to dissolve into each other.
Water.
Okay, sure, we can do water. What do we want to dissolve into water?
Can we do heptane?
Heptane?
Yeah.
Sure, okay.
Water's pretty standard.
You don't want to do it with like heptanol or heptanoic acid or like heptene or make it any weird thing? Just heptane?
I mean, we can make it weird. I just don't really understand how to do these.
Let's do heptane to start.
Okay.
Okay, let's just do heptane. Heptane is 7 carbons. Is that right?
Yeah.
Heptane 7 carbons. This is going to be C7H16. It's going to be 2, 3, 4, 5, 6, 7. It's just going to be a wiggly line. You're all comfortable with line angle drawings? Right, so this is 7 carbons with all the associated hydrogens. First thing we have to realize before we start writing stuff down, we already knew this, but this is going to be for covalent consideration. Now, one of the nice things, one of the problems we had with our ionic solutions, and the reason we jumped straight to doing experimental observations with our ionic solutions, is it was really hard to figure out what was happening with delta H. It was really hard to figure out what was happening with delta S. So for our ionic compounds, we always needed extra information, either provided in the problem or experimentally measured. For covalent compounds, we have a little bit more we can say about what's going on. So one of the easy things to say here is if I've got a water molecule, I'm going to try to draw my water molecule relative size. Right? So that would be the size of my water molecule approximately. Right? I got my oxygen, if I draw the hydrogens on there, it's like too big, but that's like the size of a water molecule compared to my heptane. What's the delta S if I mix two pure solutions? Water is pure, heptane is pure. I mix them together. Entropy does increase, decrease, stays the same. It's increase. Wait, what'd you say? Oh no, it's increase. Right, so when we think about this, 2 containers. I'm going to switch the color of my heptane molecule real quick. We're going to make heptane green. Okay. Right, so here's my water, here's my heptane. For simplicity's sake, I'm going to make my water molecules a bunch of dots. I'm going to make my heptane molecules a bunch of lines. They don't have to be going the same direction, but I've got my heptane molecules, I got my water molecules. Right, this would be their solutions by themselves. Like this, the pure water and the pure heptane, they have some entropy, right? Those molecules can tumble around in different directions. They have some ways they can rearrange. But if I mix them together, I need a bigger container to mix them because it's 2 solutions. Right? More jumbled. Can I draw the picture a different way? Can I draw the picture more different ways than individually? Right? That more ways to draw it, that more ways things can arrange, that's what tells me delta S is going to be positive. If they indeed mix, I would get an increase in entropy. Do they actually mix? We could do an experiment, see if water and heptane mix. That gets us experimental information about delta G. But before we go do that, we can look at this and say, well, what's the enthalpy of this situation? How can I tell the enthalpy of mixing these 2 things together? And that is where we start to use that idea of intermolecular forces. So what I'm going to do is I'm going to look up the intermolecular forces of these 3 things. And that intermolecular forces is going to give us an idea of the delta H of solvent, the delta H of the solute, and when I put them back together, that's going to get me the delta H of mixing. And I can estimate these different things from the intermolecular forces water has that I have to deal with, from the intermolecular forces that heptane has that I have to deal with, and then the intermolecular forces we get back from mixing them together. Does that make sense? So I say, okay, let's think about water first. We think about water pretty often. It's an easy one to think about. So I'm going to make a little chart over here. I'm going to make sure it's on camera. Okay. So I'm going to make a chart over here. I'm going to do H2O. Hopefully I've got enough space here. I think I've got enough space. Okay, so I'm going to do London dispersion force, dipole, hydrogen bonding force. I want to look at it for H2O. I want to look at it for C7H6. And I want to look at it for the mix of the two. So if I just look at water, does it have London dispersion force? Of course, everything has London dispersion force. It's kind of a small London dispersion force because it's kind of a small molecule. Does it have dipole-dipole interactions? Yeah, of course it does. We know this about water. Does it have hydrogen bonding force? Yeah, it does. What this tells me is the delta H of the solvent, I'm going to have to put a lot of energy in to push the water molecules away from each other, right? 100 degrees Celsius to get it to boil, right? That means I have to put in a lot of energy, so that's going to be a pretty big positive. So, got to put in a lot of energy if I want to make space between my water molecules for the heptanes to sneak in. I'm going to have to put in energy to get the water molecules separate from each other so the heptane can sneak in, right? To get these lines in between the water molecules, I have to make space between the water molecules. Making that space is really expensive. I have to put a lot of energy in to make that happen. What about making space between the heptane molecules so the water can fit between them? I've got my big heptane molecules. I have to just make space between them for the water molecules to fit between. To figure out how expensive that's going, it's still a cost, it's still going to be positive, but how expensive is it? Does C7H6 have London dispersion force? Yeah, and it's got a pretty big London dispersion force. Does it have dipole-dipole force? Nope. Does it have hydrogen bonding force? Nope. So in this case, it's going to be a pretty small positive. Even though that London dispersion force is large compared to water, London dispersion force is still really weak. Question?
Can something have hydrogen bonding without dipole-dipole?
For our class, no. Right? There are weird situations where you can. It's something that can accept hydrogen. So this was something I talked about briefly in class about things that can accept hydrogen bonds versus donate hydrogen bonds. It gets a little bit more technical than we really need to talk about this quarter. But it's kind of like half yes. It's not exactly completely yes. Pure solutions, I don't think so. But if we're doing mixtures, kind of yeah, there's weird situations we can have like that. So now I say, okay, it's going to take some energy to make space between my molecules, but it's not going to take a lot of energy for heptane. Heptane's boiling point is really low. Like, could you all smell the heptane in the room when you were dealing with it? That's because even at room temperature, it's already starting to move away from each other. So much lower energy in order to get it to split up than we see for water. Now we say, okay, well, when we mix them back together, how do water molecules interact with heptane molecules? Are water molecules going to be able to hydrogen bond with heptane? No. Right? Heptane has a bunch of hydrogens, but none of them are polarized. None of them have a slight positive. So even though it has hydrogens, we have specific conditions necessary for hydrogen bonding that heptane does not meet. So we get no hydrogen bonding force. Do we have any dipole-dipole interaction between water molecules and heptane? No. Technically, we can have dipole-induced dipole action. That would give us a slight change, but that's pretty weak. It's not going to be a major consideration here. Does exist. It's part of why if we were doing this from a numerical standpoint where we're actually trying to calculate the energies, we would be a little bit off if we didn't include the dipole-induced dipole effect, but we don't need it here. Do we have London dispersion force? Of course, everything has London dispersion force. But notice the water molecules interacting with the heptanes, it's going to be like a lot of water molecules to interact with one heptane. So we end up getting less London dispersion force back out than we'd have to put in. So the energy that I get back out when I put this all together, when I put them back together, I get energy out, but I'm getting like a really tiny amount of energy back out. I'm not getting a lot of favorable interactions. Does that make sense?
Yeah.
Okay.
Wait, so for the...
There's one more step, but go ask your question
okay,
first.
No, I was just gonna ask, like, for the first column and then the second column, like, if there's dipole in one and then nothing in the other, would there ever be dipole in the mix?
Nope.
Okay, so basically, in order for the forces to exist in the mix, it has to be in both the molecules?
Yeah.
Okay.
Yeah. With the weird exception of you can have weird things where there's like hydrogen bonding force in the mix that you don't have, but those are unusual. I'm not going to put those on like quizzes or exams.
Okay.
Just know that we're getting like 90% of the answer with like 20% of the work. Could we do a lot more and get more detailed? Yeah, this is going to be close enough. So yes, for us this quarter, yeah, that's totally fine.
So like, in order for them to mix so that the plus and minus balance out, then basically all the forces have to like,
line up.
Okay.
Yeah. This is where we get the idea of things. So this is the 124 idea of things with similar intermolecular forces will be soluble in each other. Or if you go back to high school, I'm going to say the thing I don't like dissolves like. Now, if you think like dissolves like in terms of intermolecular forces, I'm okay with it. But if you're just thinking polar compounds dissolve other polar compounds, too simple. Because when we start getting to larger molecules, we can have things that both have polar ends and nonpolar ends. So do you call it polar or nonpolar? Right? Polar actually has a specific definition to it of being soluble in water. So polar compounds dissolve in water, nonpolar compounds don't dissolve in water. So when you say like dissolves like, you're really just saying things dissolve in water that dissolve in water, and things that don't dissolve in water don't dissolve in water. It's not as useful as it sounds when you know the definition of polar. That's why part of when I talk about this in 124 and what I talk about here is I talk about permanent dipole moments, which typically make polar compounds, but not for sure. Okay, last step for our delta H is our delta H is going to be solvent plus solute plus mix. Big plus a little minus. Delta H is going to end up positive. I just add those three together. Big plus, little minus is a big plus. I'm going to have to put energy in to get heptane and water to mix. Now, when we look at this, we say, oh, I'm going to use purple again. Don't judge me. When we look at this, we say, oh, you know what? I actually can't say much about delta G, because delta G is delta H minus T delta S. If delta S is positive and delta H is positive, right, it should be temperature dependent. Big temperature like delta G is generally going to be positive, but if the temperature is really big, this negative T delta S term could become more important. So really it should be temperature dependent. However, we all did the experiment yesterday. We saw water and heptane don't mix. So we know this delta G is going to be positive. And I'll put a little note. Right. It's going to be positive unless there's a weird temperature. And what I mean by weird temperature is, in theory, if you get to a high enough temperature, you can get heptane and water to mix. I'm not sure, we'd have to do a calculation to tell, but I think that temperature is past water's boiling point, or close to. So we'd have to essentially boil the water in order to get them to mix, which is not going to work. Plus, heptane would start to volatilize off before, since heptane is easier to boil. The heptane would volatilize and boil off before we'd get to that point. Other ways we could get them to mix temporarily, right? We got to put some energy in to make this happen. So shake it up, right? Same thing you do with salad dressings. You get your oil layer, you get your vinegar layer, you shake it, you can get them to mix, but as soon as you stop shaking, it starts separating again. Because the delta H term is more powerful than the entropy term. Mixing would increase the entropy. But remember, entropy is on the scale of joules, enthalpy is on the scale of kilojoules. So you'd have to get really high temperatures, or put in lots of energy somehow to get them to mix, to overcome this enthalpy term. For covalent compounds. So some of the important differences. For ionic compounds, we really couldn't say much about delta H or delta S, but it was easy for us to experimentally observe delta H and delta G by saying whether it was soluble or insoluble and seeing whether the temperature went up or went down. And that allowed us to figure out what was happening with delta S by making experimental observations. For covalent compounds, we can use our molecular structure knowledge to really get at this delta H idea. And as long as we're mixing pure stuff, we already know this delta S is going to be an increasing value. So by knowing stuff about the molecular structures, we have more knowledge before we go into it, before we go into the experiments. Now we could go, I don't think, we didn't do a temperature probe on water and heptane, did we? There's a few where you do temperature probes. I don't think you did this one, right? Because this one's weird. If we had our temperature probe in water and then we poured heptane on top, it's not actually going to mix. We're not really going to see this delta H happen. So because it's not going to happen. But this kind of tells us why it doesn't happen, why we see this non-mixing. For me, here's what's more interesting. This explains why things do mix, right? Oil and water don't mix. They say separated because they don't have similar IMFs. But why do water and ammonia mix? Why do water and ammonia mix? They have similar IMFs. Why don't they just stay with themselves? Right? The ammonia's already got favorable interactions with the other ammonia. Why would it go and trade those interactions with the water?
Because they're stronger bonds?
No. It's about the same interactions. It's not the delta H. It's not the enthalpy. It's the delta S. It's the entropy. Right? By having our water molecules and our ammonia molecules mixed up with each other, we increase our number of microstates. We have this entropy increase. Our delta H is about 0. That positive delta S makes it happen. So here's the cool thing about entropy. We now understand why things mix up because of entropy. Right? The reason why things mix and why we can get things to stop mixing or we can get them to start mixing is entropy. And so we can start to make sense of that. And that knowledge lets us do other things later on.
Question?
Yeah.
So does increasing the entropy mean just like mixing it vigorously or something?
Increasing entropy means it mixes without us doing anything.
Oh, I see.
We pour them together and they just start mixing on their own. Right? I don't have to put extra energy in. Right? Because that process, so that's a spontaneous process of them mixing. Because the process of the mixing increases the entropy, increases the number of microstates. So essentially dissipates the energy, lets the energy spread out between the materials better. Other question?
If the IMFs lined up, would a big, like, if you have like a really big hydrocarbon with like a small molecule, would that LDF difference be enough to make it so they don't mix?
Not really.
Okay.
Right. I don't know if you remember the LDF range. If you got really large molecules, maybe. I'm talking like polymers, DNAs, like really large things. Maybe that could have an effect. But the LDF range is like 0.01, which is like tens of joules, up to a really large value. But the typical range for London dispersion force is from like 0, not really 0, like from 0.01 up to like 2 or 3 kilojoules per mole. So it could have an effect. I think at room temperature, this would actually be a really interesting thing to test. I don't know if other people have done this, but at room temperature, I think the entropy term would be big enough that they'd mix. but can we figure out the size of the London dispersion force by tweaking down the temperature until they separate and figure out the temperature at which delta S and delta H are about equal to each other? And is that how people figure out the London dispersion force energy of a molecule? Because I've actually never looked at that experimentally, but I think we might have just found a way to do that. So maybe if we brought the temperature down enough so that entropy term was less and less important, but at room temperature, I don't think LDF differences would be big enough unless it's really big, like proteins and polymers. Outside the scope of this class. But interesting question. Good question. I think I heard the bell. Is it 3 already?
It's 3:12.
Great. I'll still answer any last minute questions. I'm still recording. I'll still answer questions before we get going. Anything else we want to talk about?
I have a question. On the other lab we did this week where we were measuring the temperature of mixing solutions, how are we supposed to find the numbers? So like, how are we supposed to find the delta H when we mix the solutions, or the delta S or the delta?
Oh, so in those cases when we were measuring temperatures, it's this idea of delta H is positive if the temperature went down, delta H is negative if the temperature went up. So it's just the sign of it, not the exact number.
Oh, so it's just asking for a sign?
I'm pretty sure.
Oh, I need to read more. That's why.
And then your question?
I just have a question on the homework. I think it was from point 1, but
Okay.
it's considered a chemical reaction. It's H2O liquid goes to H plus aqueous plus OH minus aqueous.
Uh-huh.
And what is the sign of
Thank you.
delta
You bet,
H?
see it. Delta S, delta G.
No, it just asks for delta H, but then it says a different reaction has. Oh, this is kind of like a separate question. It says delta H is greater than 0 and delta S is less than 0. When will delta G be negative?
Oh, okay. Yeah, so that's two different questions.
Yeah.
So
but
we're
just
doing-
the first part.
Okay, let's think about H2O going to H plus. Let's erase this and do that one real quick. Do you got the number on that one? Hey.
Like the question number?
Yeah.
It's 25.
On 3.1?
Yeah, I think so. Yeah.
Okay, so we're looking at H2O liquid going to H plus OH minus.
Mm-hmm.
This is a really, really important reaction. This is referred to as the autoionization of water. I usually write it a little bit different than this, but we'll go with it this quarter because we haven't learned Bronsted-Lord yet. Okay, and so what did the question ask for delta H?
It just asks what's the sign of delta H.
Ooh, what do you think the sign is going to be?
I don't know, is it negative?
I think so.
Okay.
Why did you think negative, besides it's a 50-50 guess?
I did kind of guess, but I guess it's like breaking apart into ions.
Mm-hmm.
So it's like releasing energy.
Yeah, so there's a couple different things that we can think about for what's going on here, right? It's a little bit tricky. Does it give us any more context?
No.
Okay, so if I'm thinking about this in terms of the same kind of IMF interactions that we're thinking about, this has hydrogen bonding force, this is ion dipole interactions. So when I look at this, I'm going to end up with stronger IMFs at the end. So the fact that I'm ending up with stronger IMFs at the end means that I would look at this like a delta H positive on this side and a delta H negative on that side. Not doing it like a reaction, doing it like a mixing, I would say my delta H of solution would be like a small positive plus a bigger negative. So I think it would be overall negative. We could also, that's one way to think about it. I also like your way of thinking about it, where we could think about it in terms of the, we can also think about it in terms of the delta H of formation of the products minus the delta H of formation of the reactants. Right, and one of the things that people have had a lot of trouble with at this point is paying attention to when we use which consideration, right? This is two different ways we can think about the delta H of this reaction. Do we think about it in terms of IMS, or do we think about it in terms of the delta H of products and reactants? I actually feel like the black writing is the better way to think about this one, for this question, because we're not really making a mixture. It's not like we have water and we're mixing H pluses into it. We're really kind of doing a chemical reaction here where bonds are breaking. So I feel like the products reactants way is a little bit better way to go about it. Now, inside of this, we have to think about, and that's why I asked if there was more context, because I feel like a little bit more context would push me more towards this. But the fact that, like, this idea of the delta H of solution, that's really mixing two things together. And this is taking water and breaking it apart. So what's happening here is my HOH, like, essentially this bond breaks, the electrons hop over this way, and I end up with H plus and OH minus. And so I break a bond there to make that happen. The reason I'm like, ooh, this could be tricky is because then I should have a bunch of other water molecules. I drew it the wrong direction. I should have some extra water molecules come start to hang out with this guy. So those IMFs that I get back out might make the energy lower than the hydrogen-oxygen bond energy. It actually is definitely going to make it lower than the bond energy, which is why we switched from using bond energy to using enthalpies of formation. But I think we just use the enthalpy of formation method. But we still have an idea that's like breaking a bond, so I think it's going to be, ooh, actually, hold on. If it's like breaking a bond, that would be endothermic. But we get these interactions back out afterwards, that would be exothermic. A little tricky to predict. I think it's going to end up being exothermic, slightly exothermic.
Okay.
But a little bit tricky. I can't quite tell. From the IMF's consideration, I think exothermic.
Okay.
But in my IMF's consideration, I didn't take into account that bond breaking. So maybe endothermic.
Okay.
The point is, you know, this is a tricky one. Doesn't give us any other hints or tips. Can I read the problem real quick?
Yeah.
Okay, so a process increases the entropy of the system. Wait, which? Oh, this one. Consider the chemical reaction H2O. Consider the chemical reaction H2O goes to H plus equals. And it's got positive or negative as the only choices. Oh, or unknown. So, like I said, this one's tricky to predict. I don't know what the right answer is. I'm leaning towards unknown now.
Okay.
Right? I know it's not zero. If it's zero, that's a weird coincidence.
Mm-hmm.
And from the information provided in the problem, I can't tell if it's positive or negative. If I wanted to, so now, if this wasn't a graded problem where I was trying to do it in the context, what would I do next to figure it out?
Would you find like the delta S and all of that?
I would just look up the table, delta H. I would just do sum of products minus sum of reactants and figure out what the delta H for the reaction is, then I'd know. And that's why I want to see the context of the problem. Does it say like use the database, does it use the appendix, use the database? And it doesn't. And if it did say use the database, use the appendix, I think it'd have a box for putting specific numbers in. So from those little like problem setup hints, I might go unknown on this one.
Okay, should I like check the table or like the list to like see? Or
We could out of curiosity.
okay.
Yeah, but just from the idea of bonds breaking, new interactions forming, and if it weren't ion dipole interactions, which are pretty strong interactions, I'd feel pretty confident. But the ion-dipole interactions are pretty strong. So that's where it gets tricky.
Okay.
Okay. I'm going to go ahead and stop recording.